Hello everyone, welcome back. All right, today we're going to have a little discussion about forces and net force and what it means for things to be in equilibrium. All right, so equilibrium is a special word that we typically use here in science classes. And equilibrium always means a state of balance where things are balanced. And depending on what class you're in and what you're discussing, equilibrium can mean different things. But we're talking about forces in this unit. So when we talk about equilibrium, we're talking about a state in which all the forces on an object are balanced. All right, and so if we have balance on forces and they're all canceling each other out, and that's essentially what balance means, then they should all add up to nothing. And that's what net force is 0 newtons really means. All right. So we can think about this conceptually, where we're talking about a balance of forces. And then we can also talk about this mathematically, where we're saying that all of the forces that are acting on the object, they're going to add up to nothing. All right. So then we have to ask the question, if I have an object that's actually in equilibrium and I'm looking at it, what is it actually doing? How does it behave? All right. And essentially, we can say that objects that are in equilibrium will not accelerate. All right. They will not accelerate. How do we know this? Well, Newton's second law tells us that if there is a net force that's acting on an object, it will cause an acceleration. But in equilibrium, there is no net force. So there is no acceleration. All right. Net forces cause accelerations. All right. So what is it that we're looking at? What type of motion is it? What does the object do? Well, first, objects that are stationary would be in equilibrium. All right. So if an object is stationary, then all the forces on it are balanced, then it just doesn't go anywhere. But also objects that are traveling with a constant velocity would be considered in equilibrium as well. All right. And this one is a little bit stranger, but if we look back at Newton's first law, we see both of these situations. Remember, Newton's first law tells us that objects that are at rest will remain at rest unless acted upon by an outside net force. So here we're talking about stationary objects, and we're saying that they're going to stay stationary unless there's an outside net force. Well, since we're saying that there is no net force, then the object will remain stationary. All right. Likewise, the next part of Newton's second law says that when an object is traveling uh, in a state of motion with a constant velocity, that it will remain at a constant velocity unless acted upon by an outside net force. All right, this is by virtue of its inertia. So an object's inertia will continue keeping it moving at a constant velocity, even when the forces that are acting on it are balanced and cancel each other out. All right, so this is what equilibrium looks like. Um, and this is what we're going to be looking for as we're actually doing problems. All right. So when we go to do problems, we're going to use these key words and key situations to help us know when we're actually going to use 0 newtons for our net force. All right. Remember how important 0 was in previous units. You know, when we had to know when the initial velocity was 0 or the final velocity was 0. Those were very special times and special things, and they were very important for the calculations that we were doing. Well, this is the same kind of situation. We want to know when the net force is 0 so that we can use it in our calculations. All right. So in our first example here, we have a 30-kilogram object that's moving to the right with a constant velocity. What is the normal force that's acting on the object? All right. So every one of these problems, we're going to start the same way. We have an object that's on a surface. It's moving to the right. Okay. What forces are acting on this? So we're going to draw our free body diagram. We have a gravitational force that's pulling down, all right? And since there's a surface, there's a normal force that's pushing up, stopping that object from moving down through the surface. Now, even though the object is moving, there is no applied force pushing this to the right or to the left. Why? Well, it's traveling at a constant velocity, all right? And when there's a constant velocity, that means that all of the forces are balanced, all right? And there doesn't need to be a force. If there was a force there, it would be unbalanced and it would accelerate. But that's not the case here. So one of the things that we can say is that the net force in each of the directions is going to be 0 newtons. So why is this the case? Well, first, Remember, net force is the sum of the forces. So in the horizontal direction, right, there are no forces acting on this object. And so clearly they have to add up to 0 because there's nothing there. In the vertical direction, though, gravitational force is pulling down, the normal force is pushing back up, but this object is moving with a constant velocity, and we know that objects move at a constant velocity when they are in equilibrium. And since it's in equilibrium, we can say these things have to be 0, all right? So constant velocity those keywords are telling us why our net force is 0 in this case. So since it means it's in equilibrium, that means we can automatically say in our calculations that the net force in each one of those directions is 0. So our next step is to actually write the equation for this problem. And each time, we're going to have to write the equation specific to our picture. All right. So we draw our free body diagram, and then we write our equation based on our picture. All right. Now in this picture, we only have vertical forces. So I'm going to do the net force in the vertical direction, the y direction, and then I'm going to add up all the forces that I see there. So in the vertical direction, I have the normal force, and I have the gravitational force. So I have this equation, and this is what I'm actually going to use to solve for the normal force. All right. Now I know that the net force in the y direction is 0. So I can substitute that value in for the net force in the y direction. Sweet. I'm looking for the normal force. Now I just need the gravitational force. All right. Now I have the mass of the object, but I don't have the gravitational force. I can calculate it, however. So I'm going to do that as a separate calculation. I'm going to find the gravitational force, or the weight of the object. All right. So I'll take that mass of 30 kilograms, and I'll multiply it by 9.81 meters per second squared to get a gravitational force of 294.3 newtons. All right. So I'm going to use that as my gravitational force. But in my picture, the gravitational force is pointed downward. And we know that down is in the negative direction. So I'm going to use a negative 294.3 newtons when I substitute it into this equation. Well, now I have all the variables. All I have to do is add 294.3 to both sides of the equation, and I should get my normal force to be 294.3 newtons. Well, I know this seems really silly. It's the same number, right? Why is it the same as the force of gravity? Well, we're saying here that the gravitational force and the normal force are balanced with each other. These are two forces. They're balanced with each other. And the only way the two forces can be balanced with each other is if they have the same value, the same number, the same magnitude, 294.3. But they have to be in opposite directions. So the gravitational force is a negative 294.3 newtons, and the normal force is a positive 294.3 newtons, right? And so together, they are going to cancel each other out, and they're going to give us a net force of 0 in that direction. That'll give us our balance that we're looking for. So the normal force counteracts the gravitational force. To cause equilibrium. The only way it can do that is by being equal and opposite. All right. So let's look at our next example. So in example number 2, we have a 45 kilogram box that's falling through the air at a constant speed. What is the force of air resistance that's acting on the box? All right. So I'm going to draw my free body diagram again. So here I have a gravitational force again. All right, but I don't have a normal force this time because there's no surface. So what I'm going to have instead, what's resisting this thing falling is going to be the force of air resistance. All right. Now we know that this thing is falling at a constant speed, so that means that we're in equilibrium. And we can write these two little phrases again, that the net force in the x direction is 0 newtons, and the net force in the y direction is 0 newtons. All right. So because we see the words constant speed, we can say that both of those net forces are 0. Now again, we have no net forces in the x direction, or we have no forces in the x direction, so we can just ignore that, and we'll just go straight to the y direction. And so what forces do I have in the y direction in my picture? All right. Well, I have two of them. I have the gravitational force, and I have the force of air resistance. So when I go, I'm trying to solve for this force of air resistance. What am I going to need to do that? Well, I'm going to need the gravitational force, or the weight of the object, and I'm going to need to know the net force of that object as well. So I know the net force is 0 newtons, right? That came from right over here, knowing that it's at a constant speed. All right. The gravitational force, we can go ahead and calculate that again, just like we did the previous time. So we have the gravitational force, or the weight of the object. All right, in this case, 45 kilograms. And notice what I'm doing in each one of these problems. I might go off and I do some side work, right? But I always come back to this equation right here, because that's the important one. Everything is centered around that equation. All right. So for this, I get 441.45 newtons, right? So I'm going to use that here. In my picture, the gravitational force is pointed downward. So I'm going to use a negative 441.45 newtons, all right? And after a little bit of algebra, I determined that the air resistance is pointed upward with 441.45 newtons, all right? So when an object falls through the air, it'll begin to accelerate for a while. But eventually, air resistance starts to push up with the exact same amount of force as the weight is pulling down. And when those two forces are equal, when those two forces are balanced, the air resistance and the gravitational force, then we're going to fall at a constant speed. This constant speed is what we call the terminal velocity of an object. So there is a set number when something falls through the air that it can't go faster than that just because of gravity. All right. All right. So for our third and final example of balanced forces, we're going to add in some extra stuff here. Here we have a person applying a force of 45 newtons to the right on a 70 kilogram box that's on the floor. If the box travels with a constant velocity, all right, constant velocity keywords, that means we're in equilibrium. What is the force of friction? All right, so we're looking for the force of friction. And what is the normal force on the box? Now, I don't have equations for friction or for normal force. I have to write them. All right, so I'm going to start by drawing my free body diagram. All right, so here I have gravitational force pulling down. I have a normal force because I have a surface that's pushing up. I also have an applied force off to the right. That applied force is this 45 newtons from my problem. All right, so that applied force is pushing off to the right, but if this was the only force, then that would be unbalanced. What's balancing it out? The force of friction in the opposite direction. All right. So all of these forces together are causing this box to be in equilibrium. How do I know it's in equilibrium? Again, constant velocity. So I see that means that my net force in each direction is going to have to be 0 again. And I'm going to write my two equations. All right. So I'll start with the horizontal direction. In the horizontal direction, I have two forces. I have the applied force, and I have the force of friction. So I'm going to put them both into my equation. In the vertical direction, I have two forces. I have the normal force, and I have the force of gravity. So I'm going to include those in my equation. So two directions, two equations. All right. So I'll start by solving for the force of friction. That's right here in the first equation. To be able to solve for that, I'm going to need to know two things. I'm going to need to know the applied force, and I'm going to need to know the net force in the x direction. I know the net force in the x direction is 0 because it's in equilibrium. I also know that the applied force is 45 newtons to the right, so I'm going to use a positive 45 newtons in my equation. And then I can just go ahead and solve for the force of friction because I have all of the other variables in that equation. And so I end up with negative 45 newtons, or in other words, 45 newtons to the left. Now, if we would have really thought about this, just looking at our free body diagram, we probably would have already known this answer. That if the applied force right over here were 45 newtons, then the only way that this force could be balanced is if the force of friction were exactly the same number, 45 newtons, but in the opposite direction. So yeah, we did all of these calculations to show that. But I guess we didn't really need to. Conceptually, we could have also determined that same thing, that those forces would have had to have been equal. We can also get the same knowledge from the normal force and the force of gravity. The only way that these two are going to balance each other out in the y direction is if they're the same value but in the opposite direction. Mathematically, we see that that actually happens. All right. So I substitute my 0 newtons. All right. I can calculate the gravitational force on my 70 kilogram box. All right. And I end up here with negative 686.7 newtons for the gravitational force. You can do that work on the side. All right. And that means that I get a normal force of 686.7 newtons, which is exactly opposite my force of gravity to cancel those out. And that's how we end up in a state of balance. All right, so in summary, all right, objects that are in equilibrium, all of the forces are balanced on them, all right? These objects will not accelerate because Newton's second law tells us that the only way that an object accelerates is if there is a net force that's acting on it. So what will we see? These objects are stationary objects, or they're objects that are traveling at a constant velocity. So when we see those words, we know automatically that we can use 0 newtons for the net force in both directions, the x and the y directions. And there you have it, guys. That's how you do balanced forces.